So in this video we're going to discuss time of flight mass spectrometry. Now chemists need different ways to analyse samples that they've found or made, and one of the techniques that we use in chemistry to analyse our samples is called mass spectrometry. What it does is it gives us information. Generally most of the information it gives us, if you think about the name, is it's about the mass. So we're going to break this down into stages. There are 4 key stages to know about for the exam, but that first stage, ionisation, is going to be our most important stage. So what we're doing is we're going to inject our sample into our mass spectrometer, and we're going to now take a closer look at ionisation. So we're going to take a closer look at this section of our mass spectrometer, this ionisation area. Now AQA want you to know about 2 types of ionisation. So we're going to have a look at both of those types. The first type that we're going to look at is going to be called Electron Impact Ionisation, or just electron ionisation, sometimes referred to as EI. So we've zoomed in on that ionisation area. How would it look for electron impact? So here we are, we've zoomed in on that ionisation area, and what we've got going on is our sample is being injected from the left hand side. So we can see this dotted line is our sample passing through, and what we've got here is we've got this electron gun. So it's that's a fancy name for something that is just the hot wire filament. If you imagine an old-fashioned light bulb and you've got that little wire filament wrapped round, and it gets really hot, and when it gets really hot it emits electrons. Now if in the middle of there our sample is passing through, and our sample, maybe it's an element, has got some electrons in the outer shell, as these electrons that are flying through here, if one of them hits that electron, then that might get knocked out like a snooker ball. So the white ball bangs into the red snooker balls, and it's going to knock one of the red snooker balls off, so an electron gets knocked out. As a result, our M is going to turn into N plus, because it's becoming an ion, a positively charged ion, and it's losing that one electron that's being knocked out. So if this electron gun is firing electrons across this gap, and there's a positive plate at the other end to attract the electrons from the electron gun, then if an electron is knocked out, our sample is going to become positively charged, and we attach the negative plates of an electric field, which is going to be part of the next stage, are attached at the end here, and so the positive ion is going to be pulled in this direction. So the positive ions are going to get accelerated by an electric plate. This acceleration is actually the next phase, but you could imagine now they're going to be pulled to the right because we have got this negative plate here, and that is going to cause our acceleration. So electron impact is we're going to take our sample. So if we were putting an element in here, so for example we put some sodium element in, as it moves through the machine, at this point it gets banged into by an electron from the electron gun, and it becomes a positively charged ion, and an electron is lost, and that is called ionisation. I have made a positively charged ion from my element. If it was a small molecule, because electron impact is used to determine relative atomic mass of elements, but it's also used to determine relative molecular mass of compounds. So say I put some methane in, as it goes past that electron gun, it will lose an electron also, so it becomes CH4 plus gas, plus an electron. Ionisation. So this is called electron ionisation. We're using high energy electrons to knock off an electron, and you need to be able to describe that in an exam. So you need to be able to say high energy electrons are used to knock off an electron and create a positively charged ion. So our second type of ionisation, when we zoom into that little ionisation chamber, is called electrospray ionization, and rather than small molecules, this is going to be used for large molecules. So we might be talking about in our second year the structure of polymers, the structure of proteins, they might be determined by electrospray ionization. So we tend to use this for larger molecules. Now it's slightly different. So our sample is coming in and we're injecting it through a hypodermic needle, a very, very small needle. And that needle is connected to the positive plate. So this is the positive end of a high voltage power supply. And the negative end of that power supply is at the plates on the right hand side. That was actually very similar to in our other technique. There were negative plates on the right hand side. Here the positive plate is actually attached to the hypodermic needle. Hypodermic needle is a very fine needle, capillary tube size, very small needle. And you're going to put your sample, so some key differences that you would probably be expected to talk about in the exam. Your sample is dissolved in a volatile solvent, but that solvent is also a polar solvent. So it's polar, such as water, that's a polar solvent, or methanol, that's a polar solvent. And polar means that there are charged parts to that molecule, there is not an even distribution of the charge. And so our sample is it being injected, and as it passes through here, there is a high voltage on this needle, and as it comes to the end, because of this high voltage, the particles, the compounds in your sample are going to gain a proton, and a proton in this context we mean H+, just like we did in our introduction to chemistry. We talked about words that we use. Proton, I mean H+, is going to gain a proton from the solvent. So we've got our sample going through this tube here, and as it is attached to this high voltage, it's going to pick up a proton, and it's going to leave that capillary tube in a very fine mist. So we're squirting it out of that very fine mist, and our solvent will evaporate at this point. So it's leaving in a fine mist, and our solvent is going to evaporate, and that is why it needed to be a volatile solvent, so it evaporates easily. And now we've got charged particles, and those charged particles are going to get attracted by the negative plate of our electric field, and then that is how they're going to get accelerated. So they're positively charged, and we have a negative plate, so they're going to move through. So there's two types of ionization. You do need to be able to describe them to the exam board. So let's just have a quick recap of the key phrases we need to say. So if we're talking about electron impact, EI ionization, we need to say high energy electrons from an electron gun knock off an electron to form positive ions. And so our sample M, whatever it is going to become M plus an electron. So we're knocking off an electron to make positive ions. Our second type, ESI, electrospray, we need to be able to say it's dissolved in a polar solvent, we talked about that, water or methanol, and injected through a needle. Now that needle is attached to the top positive terminal of a high voltage supply. So it's injected through a needle, the needle is attached to the positive terminal of the voltage supply, and as they leave the needle, they're going to gain a proton from the solvent. So we're going to take our M and we're going to add a proton to make MH plus ions. So the mass of these ions isn't actually going to quite be the mass of our molecule because we've added a mass of 1, but this is going to make it a positive ion. So let's go to our second area now, and our acceleration area, this area here. What's happening now? Well, we actually saw that acceleration at the end of our ionization. Remember, we saw that at the end of our ionization we had some negative plates, and those negative plates are going to be accelerating our positive ions, and they're going to give all of our positive ions the same kinetic energy. So we have that electric field, and it's going to accelerate our positive ions and give them all the same kinetic energy. So we'll just fill in those gaps. It gives all the ions with the same charge, the same kinetic energy. They're all experience that field in the same way. And kinetic energy is a half mv squared, where we know that m is mass in kilograms and v is velocity in meters per second. And kinetic energy is our energy in joules. So what happens now? Now we've ionised and we've accelerated, and we're going to separate our ions. So our next stage is our separation stage, and that's just, there's like a big gap in our machine now, a big empty space where our sample is going to be separated. So we're going to separate now. So that separation is going to depend on the mass. They're going to travel through this space dependent on their mass. So if we have a look here, we've got 3 separate ions of magnesium, these are, travelling through the machine, and one of them weighs 24, one of them weighs 25, and one of them weighs 26. And they've all been given the same kinetic energy. So it's quite logical that the lighter ones will move faster and the heavier ones will move more slowly. And the lighter ones will travel quicker through the machine. And the time it takes for them to travel this distance is called their time of flight. And that is going to depend on their velocity. So the time of flight of something is the distance it travels divided by its speed, its velocity. So the distance it travelled would have been in metres, and its velocity will have been in metres per second. And so we'll get a time of flight in seconds, and we're going to give that a little symbol T. I'll put that in there as well. So we quite logically know that lighter ions will travel faster, and heavier ions will travel slower. And so the lighter ions will reach the detector first. That is going to be our separation phase. The lighter ones are going to go faster, the heavier ones are going to go slower, and this is how this machine is able to detect things from their mass. And then our final stage is our detection stage, so we're going to have a look at that. It's our final stage, so we've ionised them, we've accelerated them, we've separated them, and now we're going to detect them. So our sample is travelling through the machine, and as it hits the detector, what is going to happen is it's going to collect an electron from this detector. It's called an ion current detector. That's going to draw electrons through this wire, and the computer is going to be able to register this flow of current. So there's going to be a flow of current, and the computer is going to be able to register the flow of current. So as they hit the detector, the sample is going to pick back up an electron and revert to its original state. The computer is going to register the flow of electrons and say, oh, something hit me, and I'm going to measure it. If lots of things hit at the same time, because lots of my sample has the same mass, then lots of electrons will be removed and a large flow of current will happen, and the computer will notice that with a bigger response. And so when we get our mass spectrum out on our computer screen, we often see these little peaks. Now, the bigger the peak at that particular mass, then the more of that sample there is. So that in this example, where I've put that bigger peak at 24, it was bigger because more electrons were drawn at that mass, and so a bigger current was detected, and the computer drew a bigger peak. The smaller the peak, the less abundant that mass is in my sample. So let's just have a look then at what we mean by that. So at the detector, it's going to record the different ions as they arrive. At the detector, each positive ion is gaining an electron. And that generates a current. current is proportional to the abundance of the ion. The greater the abundance, the higher the current. There's just a few key points. Why do we have to ionize? Well, we need to ionize so that the thing can be accelerated. Remember, it was accelerated by a positive plate of an electric field, and it needs to be ionized so it can be detected, because it was detected by an ion current detector that was giving it electrons, and without it being positive it wouldn't want the electrons. And the whole thing is kept under vacuum to prevent the sample from colliding with other particles in the air. So that's the end of the explanation of how the machine works. We'll be moving on in the next video to some calculations.